Hello. In this lecture, we are going to continue with the things that we were doing in the last lecture. That is, we were doing the topology of the complex plane, and we reached till I think connectedness. And today's topic is a small topic that was left yesterday, and that is called as a connectedness. See, connectedness as such is an important topic. You would find that the definition for domain set itself derives things from connected set only. So this is an important zone where you have to pay a little bit of attention. And let us start without wasting time. Just give me a minute. Okay. Okay. So I hope yesterday everything was fine. Open set, closed set, all these things you might have seen. And you might have even done all these things. See, because this is an important zone, you should be really focusing a great deal here. Okay. So yesterday, the last topic that we were doing, let me just write it down. Okay. And everybody knows a few things that we've already done. Let's say one of the most important conclusion that we've got in the previous session was in complex number session also was that see, whenever you are trying to visualize complex number, whenever you are trying to visualize complex numbers, it is better to visualize it on R square. So basically, it is better to visualize it on R square. Why? As I told you initially also that there exists a field isomorphism from set of complex numbers to the complex plane, that is the R square. Okay, so this is quite evident. This is one of the important learnings from the complex numbers that you have to keep in mind. Because see, whenever some complex number is given, if you make some map or if you make some diagram, then visualization would become quite easy for you. Okay, so that's what is be taught. That is what is taught also in standard 11. That instead of writing 3 plus iota 4, you should visualize it in the form of point in the complex plane. So I'm just a little bit of revision to what we have done in the first 4 lecture. So in first 4 lecture, most important concept that uh, uh, you should keep in mind is that visualization of complex numbers in R square. So you have to remember this. And mathematically, why does this exist? This exists because of the isomorphism between what? Isomorphism between C and R square. Okay, so there exists a field isomorphism between the set of complex numbers C and the complex plane. So I would write here set of complex numbers. And here I'll write just for the sake of writing, I'm writing it. Otherwise, I've already taught you all these things, and this would be complex plane. I told you that as I go along, I'll not let you skip. I'll not let you forget all these things that you've already done, because people tend to go further and then they start forgetting what they've already done. So one of the important and one of the important results that, or probably one of the important learnings or outcomes from first 4 lecture was that if you want to really work very nicely with the complex numbers, it's better to visualize them on the complex plane. And why can we do so? Because there exists a isomorphism between C to R square. Okay, so what I can do first, let me prove it. So let's say that phi z is equal to what? Phi z is simply x comma y, where z is equal to what? X plus iota y. Let us consider this mapping and let us see how does thing work. So let us consider the mapping. So let us consider the mapping defined by phi z is equal to x comma y. So x comma y is an element in R square. So what does it do? It takes a complex number, it returns us a point in the complex plane. So what I can do, I can take two numbers. Let's see, z1 belongs to C, and let's say z2 also belongs to C, and let's say z1 is equal to x1 plus iota y1, and let's say z2 is what? Z2 is equal to x2 plus iota y2. So phi of z1 plus z2 would be what? Phi of z1 plus z2 would be phi of x1 plus x2 plus iota y1 plus y2. Okay, and that will give you, I think, x1 plus x2, and you can write it as comma y1 plus y2. And you know that this is equals to what? This is equals to x1 comma y1 plus x2 comma y2, and you know that x1 comma y1 you can write it as phi z1, and this you can write as phi z2. We'll see that this mapping is 1, 1 and on 2 also, but let me first uh, verify two of the things. So next thing would be, let us verify phi z1 z2. What is z1 z2? You know that it is equals to phi of x1 x2 minus y1 y2 plus iota x1 y2 plus x2 y1. You have to multiply the two complex numbers, and from here you get x1 x2 minus y1 y2 comma x1 y2 plus x2 y1. Okay, so this is how you are going to get it, and this you can simply write it as, you can simply write it as x1 y1 into x2 y2. I think this you can do, because you know that x1 plus iota y1 into x2 plus iota y2 is this, and clearly this is equal to phi z1 into phi z2. Next, we have to prove that whether this is 1 1 or not. So in order to prove 1 1, how do we do? We take any two complex numbers z1 z2, and we see that phi z1 is equal to phi z2, and if it implies that z1 is equal to z2, then we say that the mapping is 1 1, and that's quite easy to see. So if I write phi z1 is equal to phi z2, what do I get? I'll get that phi of x1 plus iota y1 is equal to phi of x2 plus iota y2, and this implies what? It implies that x1 comma y1 is equal to x2 comma y2. Since these are ordered pairs, you know that it is equal only if x1 is equal to x2 and y1 is equal to y2, which implies that z1 is equal to z2. So the mapping is 1 1, and for every x comma y, you have a pre-image x plus iota y. So obviously this mapping is onto also. So therefore you can say that the phi is a field isomorphism from C to R. Field isomorphism from C to R square. So one has to remember this thing, that whenever you are visualizing any complex number, you just have to see it as a point in the complex plane, and things will really become very easy for you. Otherwise, it becomes typically hard. Okay, it becomes very hard. So for example, let's say I give you one of the things that, let's say I want to know what would be the, just giving you a little bit of example, what would be the image of z, uh, image of imaginary part of z equals to minus of 1. How would this image set look like? This is imaginary z equal to 1. So what does it mean? It means that if in a plane you are considering the points with with an equation that is imaginary part z is equal to minus 1. So what is imaginary part z equal to minus 1? It is equivalent to y is equal to minus 1, right? And what is y equal to minus 1? This is how you write y equal to minus 1. So whether you write imaginary part z equal to minus 1, under the transformation, and now a little bit of functions I'm using, I hope a little bit of things you know, but I think fz is equal to z square. I think this is something that you know from your standard 12th also. So this function you know. So under the transformation fz equal to z square, how would be the image of imaginary z equal to minus 1 look like? So what does it mean? That all those points which have y equals to minus 1, if I use a function that is fz equal to z square, then how would the image set look like? Okay, right now it is looking as if it is a line. You know that imaginary z equal to minus 1 is equal to what? It is equal to a constant thing, that is y equal to minus 1, and constant y equal to minus 1 would be simply a line, that straight line. Now this is looking like this. Now, if I introduce and if I map all the points under the transformation fz is equal to z square, then how would things look like? How would things look like? So you know that from, I think we have done it quite many times, that what would be z square? If z is equal to x plus iota y, then z square would be x square minus y, comma 2xy. And if I'm talking of all the points which are y equal to minus 1, then I know that if y is equal to minus 1, then this fz equal to z square would be equals to what? Fz is equal to z square would be simply, fz is equal to z square simply would be what? It would be x square minus 1 comma minus 2x, right? If y is equal to minus 1, just place x equal. Now you see, let's say this is a your plane, your input you can say, or you can say domain of definition of f. So basically this is x comma y. So it is some plane, let's say let it be named as s. Okay. And let it be named as u comma v here. So how things would look like here? So what is u? U would be equals to what? X square minus 1, because this is how it is. And what is v? V is equal to minus of 2x. And from here, it is quite easy to see that v would be equal, x would be equals to what? Minus of v by 2. And so from here, we can establish that u would be equals to v square by 4 minus 1. And which simply means v square is equal to what? 4 times u minus 1. 4 times u plus 1. So it implies that if it is minus 1 here, so all the points which were located on the line in S plane, now in S dash plane, they lie on what? They lie on a parabola. So this is how things are easy. If you visualize your complex analysis on, visualize it on R square. Okay, so that becomes a very important concept that we've already studied in our previous lecture. Just to actually remind you, I did all these things. Now let us move to something called as the connectedness. Okay, I hope it is clear till now. यहाँ तक कोई issues तो नहीं है. I don't think there is an issue till now. Is that clear? I think Tanvi is right. Is that clear? Not?
Yes, sir.
Okay. Okay. So now let us move to connectedness or some connected set. I've already written, I think, but still let me write it so that. So in general, let me just write it for once for even for R also you can visualize it, and then we'll write it for Z and everything. So I don't think that's. Just give me a minute. Okay, so let us say that, okay. Let us say that if I'm saying connected set, okay, so I'll not define connected, I'll rather define disconnected set, okay. So let S be a subset of, let's say, R also, let's say. First, let me define R, and is said to be disconnected, not connected, I'm saying disconnected, is said to be disconnected if there exist two disjoint two disjoint disjoint means what, disjoint open subsets of R. The same definition we can do for C also. So I've written the same of R. Let's say they are called as U and B, such that A intersection U intersection B. So U intersection B is 5. So this is equals to 5. The second thing that comes to mind is that S intersection U intersection B is equal to 5. S intersection U is non-phi. Third, S intersection B is non-phi. And then you can write that is contained in U union V. This is how you can express your disconnected set, not connected set. Okay, disconnected or separated set. And we usually say that this U and V are disconnections, or you can say are disconnection of S. Okay, so this is how we actually express things. So let's say I'll take one example and help you with this. So let us say A is equal to 0, 1 union 1, 2. What do you think? This is connected or disconnected? So this is a disconnected set. Why it is disconnected? You can clearly see that these open subsets, these are two open intervals, and open intervals are open subsets, open set. So you can take U as 0, 1, and you can take V as 1, 2. Clearly, A is equal to what? It is equal to U union V. So this satisfies this definition. First. Secondly, U intersection V is equal to 5. Clearly, U intersection V is 5. See, there's no such common element. So A intersection U intersection B is also 5. That's not a problem. Okay, so this is 1, this is 2, and this is something that we've already done. Okay, now also we know that if I take A intersection U, if I take A intersection U, then we'll get 0, 1 certainly, which is not equals to empty. And similarly, if I take A intersection B, it is equals to 1, 2, and certainly it is also non-empty. So clearly I can say that this A set is a disconnected set. Is that fine?
Yes, sir.
Okay. Similarly, the set of integers, it is also disconnected. It is also disconnected. Just choose anything. Let's say just choose that u is equal to minus infinity comma 1 by 2, and choose v is equal to 1 by 2 comma infinity. And you know that this u intersection v is 0, sorry, is 5. And you know that if I take a set of integers, so I know that obviously if I do this way, it is certainly non-empty. If I take intersection with v, which is also certainly non-empty. And you know that if you do the union, you can write that this z is contained in u union b. So it satisfies all the properties that are given here, and so therefore these are called as, this is also a disconnected set. The similar approach we have also applied in our the similar approach we also have applied in the what you can say uh, complex numbers also, and possibly in class I wrote it for more what you can say, I wrote it for uh, uh, a metric space also, so that it will remain uh, all the more what you can say, all the more common, all the more common, or you can say all the more general. Okay, so the same approach you can do for the same thing you can write for connected sets in C. So a set which is not disconnected is called as connected. Okay, so this is disconnected. A set which is not disconnected is called as connected. And today we'll do something called as the polygonal connectedness, or path connectedness. So that is also one other way of doing it. Okay, so another way of doing it is okay. So that part I'll help you out. Don't worry. So the point is, what was the connected in C? So let S be a subset of complex number. It is, and there exists, I think I wrote it yesterday, so just give me a minute so that I see my copy. Okay, and it is said to be separated or disconnected. It is said to be disconnected or separated. Separated if there exist two non-empty disjoint sets, non-empty disjoint sets, disjoint open sets, sorry, my bad, open sets A and B, such that S is contained in A union B, S intersection A is phi, is not phi, and S intersection B is also not phi. So clearly one of the sets that I wrote yesterday, S3, which is all Z belongs to C, such that Z minus A modulus is less than, I think it was given as A, or Z minus A, Z plus A modulus is less than A. This set would be a, clearly see, first thing, clearly see, I can write my use A set as simply this, Z minus A modulus less than A. First thing, this is an open set, right? I think this is quite easy to see that this is an open set. Similarly, set B, I can write it as Z minus A, Z plus A, sorry, less than A. This is also an open set. Clearly, this S3 is nothing but union of A and B. Clearly, this S3, if I take intersection with A, it will be certainly, it will be equal to A itself, which is non-empty. If I take S intersection B also, then it is also Z plus A modulus less than A, which is again non-empty set. And we know that if I take A intersection B, that is completely phi. So this is disconnected set. However, if we take another examples, let's say that example of S1. Now the point is this: you cannot express, if I take Z minus A less than equal to A, and and E, or means union, this is like Z plus A less than mod is less than equal to A. Now it is no longer your open set. So it is no longer open set. This is not connected. This is connected. Sorry, this is not disconnected. This is a connected set. Now another way of looking at it is to see for a connected set you need to have two open sets. Okay, you have to have two open sets in a way that you can express your complete S3. Let's say S3 I could express as A union B, and S3 intersection A I could. So if even if I take an open variant, but the point is this equality. How to justify this equality? Is that clear? How to justify this equality? Because we know that as they'll become equal, we will be talking of the boundary points. And I yesterday told that the del S is closed in C. If you remember, we told that the limit points are also the ones which lie on the boundaries also. So it is no longer a open. It is no longer an open set. So you cannot take this entirely as A. You cannot take this entirely as B now. If you want to take, you have to take open. But then you are going to, then this will not be justified, because then A union B, your S1 cannot be contained in A union B, because you are then missing the equal ones. Are you getting my point? So you cannot write it in this manner. Is that fine or not fine?
Yes, sir.
Okay. Now, in order to really understand this, one another point is that polygonal connectedness or path connectedness. So let us first think about that, and then we'll come back to these two examples again. Okay. So let us first define something called as line segment. Okay. So function, I will write here the function gamma defined from 0, 1 to C uh, uh, defined by gamma t is equal to 1 minus of t z naught plus t times z1. Okay, now clearly see this t lies from where to where? T lies from 0 to 1. So it implies that gamma t would lie between what? Z naught to z1. Is that clear? So as I'm going to vary this t, I will vary from point z1 to z0 to z1. So it really represents what? It represents a line segment. It represents a line segment joining the endpoints z0 and z1. Is that fine?
नहीं समझ आया सर, लाइन सेगमेंट की इक्वेशन होगी।
हाँ जी, देखो ना, z
कैसे?
आप t को 0 रखो, place t equal to 0, what is it equal to?
Z
Z
naught.
naught. And if you place t equal to 1, what it is equal to? It is equal to
Z1.
what? It is equal to z1. So if gamma t lies from where to where? Gamma t lies from uh, z0 to z1. So this particular thing is nothing but it is a line segment joining z0 and z. Okay, this is a definition for the line segment.
Okay, sir.
Okay, so अगर ये mod लेता मैं, then it is a circle. See, mod z0 is a circle, but this is not a circle. This is a line segment joining the points z0 and z. This is how you define the what you can say line segment, or simply a polygonal line. Sometimes we say. Is that fine or not fine? ये चीज समझ में आ रही नहीं आ रही है?
Yes, sir.
ठीक है. See, आपका gamma t where it is lying? Gamma t lies between what? Gamma t lies between z0 and z1, and it is a linear relationship. How do you visualize a linear relationship? You visualize a linear relationship with a line.
Hmm.
Is that clear or not clear?
Hmm.
Okay, so this is one thing that you need to understand. And okay, so let's say how should I explain? Let's say if gamma t belongs to, let's say, S, where S is a subset of complex number, and for each t belongs to 0, 1, for each t 0, इसका मतलब क्या हुआ? If gamma t belongs to S, for each t belongs to 0, 1, it implies what? It implies that line segment joining points z0 and z1 is contained in S. It implies this only, is contained in S. So basically, what does it mean? Let's say if S is some region, I'm writing now. Right now, I'm using region and domain, everything the way I want to. But then I'll define it lately. What is region? What is domain? We are coming up to that only. Right now, I may have used region somewhere. I may have used domain. So right now, I'm not using it in the very true sense of things. But now you're going to really understand what is the difference between saying a region and a domain. Okay, just give me a minute. So let's say this is Z0 and this is Z1. So if gamma t belongs to S, this is your S. Gamma t belongs to S means what? Gamma t belongs to S means any line which joins these 2 points belongs to S. And if line joining these 2 points belongs to S, I will write that. So gamma t belongs to S means what? Gamma t belongs to S means the line segment joining Z0 and Z1 is contained in S. Is that clear?
Yes.
It is not the only way of doing it. See, what you can do, it is not necessary that you're going to make a straight line joining these 2 points. What you can do, you can take it on intervals also. So basically what you can do, let's say I can go from here, Z1 to Z2, then I can go from Z2 to Z3, then I can go from this is Z0, no? So this I can write Z2, this is Z3, this I can write Z4, and then I can move to Z1. Now this is clearly not a straight line. This is called as the polygonal line or polygonal. This is called as the polygonal line. What it is called? It is called as the polygonal line. Now you have to define individually these small segments. What is it is called? It is called as a polygonal line. Is that fine till now? These are all definitions. Don't worry. This is not a straight line. Clearly, okay? This is not a straight line. This is called as the. It is called as a polygonal line. क्या कहते हैं इसको? It is called as the polygonal line. Let's say हमारा Z0 is here somewhere, and let's say Z1 is somewhere here. It's not necessary that we are going to make it through a straight line. We can do this way also. Z2, Z3, Z4. So what I can do, I can go from here to here, here, and then here. So this is called as the polygonal line. But this polygonal
यहाँ के ऊपर Z0 to Z2 और ऐसे डिफाइन होगा क्या?
हाँ बिल्कुल.
गामा टी जो होगा.
Individual हमको यहाँ पर भी गामा टी, इधर गामा टी, इधर गामा टी, इधर गामा टी. We'll have to define this way because this is the line segment joining Z0 and Z2. So we'll have to define one gamma here, one gamma here, one gamma here, and one gamma here. So overall, it is not necessary that you join it in this manner only. I'm trying to make a point that if the polygonal line is contained in S, so it does not only mean this. This means this. Then polygonal line means you have to reach to Z1 through different segments also. You can do that also. Okay, why I'm doing this? This is how we define the path connectedness. So just wait for a few minutes. First, understand this is the definition for the line segment joining Z0 and Z. This is point number 1. Clear? So gamma t is equal to 1 minus t Z0 plus t times Z1. So clearly, if t lies between 0 and 1, then gamma t would lie between Z0 and Z1. And this is a linear relationship. So clearly, this forms a line. Had it, okay. Is that fine? This is one thing. Yes. Now, basically, what is a polygonal line? So polygonal line is nothing but union of all these small segments, right? This is what I've written. A union of all these segments is a polygonal line. So if I'm doing a polygonal line from Z0 to Zn is a finite union of the line segments is a finite union of line segments of the form. So what I'm going to do, if I want to go from Z0 to Zn, I can stop at some points. Let's say Z1 I stopped, then I'll take a union. I'll take from Z1 to Z2, then union, comma, then I'll take Z2 union Z3, not union, this, and dash union Zn minus 1 minus Zn. So what all these things represent, these are individual line segments, and ultimately, when I do a union, I reach to this point Zn. This is how you define a polygonal line. So polygonal line is nothing but it is a finite union of the line segments. See, when I was writing gamma t is nothing but belongs to Z0 to Z1, this was one line segment, right? This is one line segment. Similarly here, this is the union of all these line segments. This union of line segment is called as polygonal line. And we say that Z0 and Zn are polygonally connected. We say that Z0 and Zn are polygonally connected if we can visualize Z0 and Z1 being connected as a polygonal segment only when when we can take certain line segments and ultimately reach to this point. So basically this line segment and this line, this line, this line, all small line segments, and ultimately what I have done, I have reached to this point. Is that clear till now?
Yes, sir.
Okay, so this is called, we'll say that Z0 and Zn are polygonally segments, polygonally connected, sorry. Polygonally connected, my bad. Okay, so these Z0 and Zn are said to be polygonally connected if Z0 and Zn can be joined by a, not polynomial line, polygonal line. Polygonal line, my bad. No, polygonal line. So polygonal line means what? Polygonal line is nothing but it is the finite union of the line segments of the form this. So this is how we say that Z0 and Zn are polygonally connected.
Mhm.
Okay.
Yes, sir.
So basically, what do we say? Okay. So if I want to say that a set S, if I want to say that a set S is a polygonally connected set, if I want to say that the set S is a polygonally connected set, when it is a polygonally connected, if any two points can be joined by a polygonal
Polygonal line.
line, okay, it's not necessary that you join from straight. You can do this way also. But then, only then we can say that this is a polygonally connected. So in other words, what I can say, in other words, if I want to say S is polygonally connected or simply connected, if and only if each pair, let's say Z, comma, ऐसा मान लेते हैं some zeta of S, each pair Z, comma, zeta, in general I have written of S can be connected by a polygonal arc or polygonal line or simply arc, polynomial लिख रहा हूँ बार बार, polygonal line oblique arc completely lying in S. So it should not leave S, it should lie in S only. Only then we are going to say that S is polygonally connected or simply connected. Okay, so for example, if I consider any open disk, okay, any
Mhm.
open disk, what was open disk? Yesterday we have discussed any open disk centered at Z0, comma, let's say delta or epsilon, है ना? So what does it mean? It means we are talking of some quantity like this. Is that fine? So any open disk is polygonally connected. Why? What we have to see? We have to choose any 2 points in this disk, and if we can join any 2 points in this disk through polygonal line, then this entire polygonal line should be contained in this disk itself. Is that fine? Only then we'll say that this is polygonally connected or simply connected for that matter. Is that clear or not clear? ये चीज समझ
Yes, sir.
पाएंगे कैसे? How would you say that? So how to say that this is polygonally connected? How to visualize or how to understand that this open disk is polygonally connected? How to do that?
Geometrically.
Either geometrically use thing or otherwise, what I can do, I'll simply use the definition. Okay, I'll not use many points. I'll only take 2 points. Okay, not many points. 2 points से भी काम चल जाएगा. Let us consider 2
Anything.
points. है ना? Just consider 2 points. ना? So let's say Z1 is contained in uh, this particular open disk, and let's say another point I'm taking Z0, which is also contained in, let's say, this open disk. Is that fine?
Yes,
Now,
sir.
any polygonal line which joins this two arc or any line segment that, it's not necessary that I always say polygonal arc. Even if I am trying to say that if I am saying that a set is connected, then any line joining the 2 points should lie in that particular uh, set itself. So if I'm saying that S is polygonally connected or simply connected, then any 2 points in this particular set can be joined by a line segment or a polygonal line, and that line must be contained in this set. Only Only then we can say that this set S is polygonally connected or simply connected. Is that fine?
Yes, sir.
Okay, now see, if I write what is gamma t, okay, what is gamma t? Gamma t would be 1 minus t. I have taken z1 and z2 here, तो यहाँ पे क्या लिखेंगे? z1 plus t times z.
Plus 3Z.
Okay, you can reverse the order also. मतलब हो सकता है if the initial point is z2 and final point is z1. If final point is z2, then and here t lies between 0 and 1. This is a equation for this. Is that fine?
Yes,
Now,
sir.
what it is, after all, what it is? After all, this open disk is what? It is centered at z0.
Yes, sir.
It is centered at z0 with a radius of del. Is that fine? So this is what you mean when I say that this is an open disk centered at z0 and with a radius del. Okay. Now, if I want to consider any line, what I'll do? If any line is contained inside this particular disk, if any line is contained inside this disk, how to understand that? What I'll do? I'll simply take the distance from z0. Is that fine? एक बार देखो इसको. So distance of any line segment from z0, I can write this way: gamma t minus z0 modulus. Is that fine? And
Yes.
z1 and z2 are any points inside it. Fine. Okay, is that clear? I'm trying to estimate this. Now, don't worry. Just think about this gamma t minus z0. Is that fine till now?
Yes, sir.
And what is gamma t? Gamma t is 1 minus of t z1, sorry, and then plus t times z2. I hope it is clear.
Yes, sir.
And you'll get a minus of z0. Okay. Okay, minus of z. Is that clear?
Yes, sir.
Okay. Now think about this. Can I write this way? 1 minus t z1 minus z0 plus t times z2 minus z0. Just think about it. See, if I take this, this is equal to what? This is the first term. इसको देखो first term. So minus 1 plus t times z0 and this term c plus, sorry, minus t z0. So this cancels. It will, what you will get simply minus z. Is that fine? अरे देखो minus z0 ऐसा लिख, and this is one. मतलब these both things are same. The one why I have done so, you will be able to understand. Is that clear till now?
Yes, sir. Yes.
देखो ना, what you have to see. This is fine. 1 minus t z1. देखो ये रहा 1 minus t z1. t z2 it is fine. ये देखो. Here it was only minus z0. What I have done, I have simply written 1 minus t into minus z0 plus t into minus z0. So basically what will happen? Plus t naught
Minus
minus t naught.
Z0.
ये जानबूझ के, so that I can invoke inequality. So this will be less than equal to what? It will be less than equal to 1 minus t. Whether you take mod or not take, that is fine because t lies between 0 and 1. So in any way, 1 minus t would be positive or 0. Modulus of z1 minus z0 plus t times modulus of z2 minus z0. Is that fine?
Yes.
Up z1 and z2 are what points? They lie inside this disk. Okay. So obviously this will be less than del and this will also be less than del. See, what does this disk represent? This represent all those complex number whose distance from z0 is less than del. And obviously z1 and z2 are interior to this. So obviously z1 minus z0 would be less than del. So after all, what you're getting? It implies that gamma t minus z0 modulus is always less than 1 minus t times del plus del. So what you'll get? It is always less than del. So what does it imply? What does it imply? I told you that if I'm writing z minus z0 modulus is less than del, it implies that all those points whose distance from z0 are less than del. So it implies what? It implies that gamma t is completely inside what? Is contained inside the disk. Is that clear?
Yes, sir.
So इसका मतलब
polygonal line नहीं बनाएगी फिर भी चलेगा.
हाँ, polygonal line नहीं बनेगी तब भी चलेगा. In any case, you have to see any segment which joins. So 2 points है तो एक सीधे segment से जुड़ सकता है. Had it been many segments, तुम्हें क्या करना पड़ेगा? Then you have to write many lines, z1, z2, and things will become very complicated for right now. Well, it implies that if you are saying that a set S is polygonally connected or simply connected, take any 2 points, just draw a line. If that line is contained in that set itself, we say that this is connected or polygonally connected.
Yes, sir.
Okay, why we are doing all these things? Because see, in one variable mathematics or sorry, calculus, we used to use domain as very simple word. Let's say anybody in the standard 12th, if say what is the domain of 1 over x, you will simply say that x should not be equal to 0, right? Yeah, if you are told that what is root over x, you would say simply x greater than equal to 0 is the domain of the set. Now here domain is a topological term, and what does it mean? It means it is a non-empty, open and connected set. Now this is a problem. If you're not writing this, this is it. This is how you define. So therefore, at times people use what? Domain of definition. So they basically use term called as domain of definition in order to remove the discrepancy. Let's say if I'm talking of domain of definition of fz 1 upon modulus of z, what do you think the what is the domain of definition? 1 upon modulus z. Clearly you would say, okay, fz is equal to what? 1 upon root over x square plus y square. And clearly it implies that you can take all r square except what? 0, 0. This is the domain of definition. But what is domain? Domain is a non-empty, open and connected set in C. Okay. And what is a region? Now, how would you define exactly region? So, abhi tak what we have done, we've used region very in loose sense. Region means region. Okay. Now, region very precisely. What does it mean? It means domain together with some, none, or all boundary points. So it is the more general term, boundary points. So if you take boundary points, then the set will no longer remain open. Okay, set will no longer remain open. So it is more general sense. Therefore, I used a region anywhere. You told me, acha, this is a region, draw a region. But I cannot use domain this way. Matlab, samajh rahe ho what I'm trying to say? If you want to use the word domain, it is strictly non-empty, open and connected set. If you take none of the boundary points and let's say it is open, then the region would be domain itself. But if you take some or all boundary points, then domain will no longer, the set will no longer remain an open set. See, if you consider some boundary points, then how come you are saying that it is open? Okay. So, the more general way of speaking is region. So whenever you are not very sure, I would use word called as region. Okay, draw a region. So for example, I told you draw a region where real part of z is greater than alpha, if you remember. But I did not use the word domain because whenever I'm using domain, one has to really clarify that it is a non-empty, open and a connected set. Only if the set is open and a connected set, only then it qualifies for the definition for the domain. Here, domain is a very topological. So this is something that you need to really remember, or you should really consider. Is that fine? So for instance, if I say again real part of z wala hi dekhte hain. So for instance, if I take a region S1 and let's say it is equals to all those z belongs to C, such that real part of z is less than alpha, where alpha belongs to R. What do you think? This is an open set. This is a domain or not domain?
Domain.
बिल्कुल domain. क्यों? Because see, what you have seen, let's say I'll take a positive alpha so that things remain easy for you. Let's say this is your alpha. So I made a simply line. Real part of z is less than alpha. What does it mean?
X less than alpha.
X less than alpha. It means that x should be less than alpha. So what does it mean? We are talking of. Okay, is that fine? कुछ गलत तो नहीं कर रहे हम लोग? देखो. All this region is, and we are not including the boundary points. So this is what? This is open. And obviously any 2 points in this area, any 2 points you take, you can always join it by polygonal arc also. So this is polygonally connected also. Is that fine? So this is both connected and open. So therefore S1 is a domain. Is that fine or not fine? ये चीज समझ में आई ऊपर से लगी?
Yes, sir. Yes, sir.
Okay,
Fine.
this is polygonally connectedness. So at times you will find lately there are two different terminologies, connectedness and then path connectedness. Right now it is fine. Right now I'm using it interchangeably. Okay, right now this is the first lecture, so I'm not getting into too much of detail, but right now, is that clear till now? And we'll do many questions. Right now the point is that I really want to introduce you to all these terminologies first. So just don't worry, we'll keep doing things at time and again. Just think about this, whether this S2, let me write it as Z belongs to C, and let me write real part of Z is less than equal to alpha, where alpha belongs to R. Is that a domain or not?
No.
It is not a domain. Why it is not a domain? It is connected, but it is not open. Since it is not open, so therefore it is not a, what you can say, domain. It is connected. That is not a problem, but it is not a open set. Is that clear or not clear? Let's say another set, let's say S3, if I take all those Z belongs to C, such that real part Z modulus is greater than alpha, where alpha belongs to R. Now tell me, is that uh, is that domain or not?
No, sir. Not
Why?
domain.
Why?
Not connected.
वेरी गुड, नॉट कनेक्टेड. ठीक है. सो राइट नाउ जो भी विजुअलाइजेशन कर रहे हो तुम पॉलीगोनल कनेक्टेडनेस से कर रहे हो, बट दैट इज फाइन आल्सो. राइट नाउ इट इज फाइन. वील सी ऑल थिंग्स वेरी डिटेल्ड थिंग्स लेटर ऑन. राइट नाउ मेरा टास्क ये नहीं है. मेरा टास्क है समहाउ यू गेट टू नो थिंग्स. ओके, सो व्हाट इज रियल पार्ट z मॉडुलस, सॉरी, रियल पार्ट z मॉडुलस क्या होगा? सो इफ z इज व्हाट, x plus iota y. Very good. So real part of z is what? Real part of z is simply x, and I'm taking a modulus of it. So what does it mean? I'm taking modulus of x. So if I write that modulus of x is greater than alpha, what does it imply? It implies x belongs to minus infinity comma minus alpha union alpha comma infinity. So what does it mean? If I'm taking alpha as a positive number, so this is how it is. So if I'm taking alpha to be positive, you can take alpha negative also, but right now it's not. Just to keep things easy. So this is how it is. This region.
Yes, sir.
And then this region also. Okay, is that clear? Now the point
Yes.
is this: both of these regions, both of these regions are open. Like you can, these are union of open intervals is an open thing. But the point is this, that this is not connected. Is that clear? You can take any 2 points. Take this point and this point. You cannot join these 2 points. I hope now it is visual clear. I think the light went, so that's all. Am I audible right now? Hello, am I audible?
Yes, sir.
Okay, so this is not connected, and therefore we can say that this is not a domain. Rather, we can say this is a region. That is not a problem, but this is not a domain. Is that fine? Similarly, if I want to write, uh, let us say another, what should I say? What about this? We'll do all these things tomorrow also, but just a few examples, and then tomorrow we are going to see in more detail, or more questions we are going to do. So if I take all those z belongs to C such that the real part of z lies between A and B, and including B, for some A less than B. What do you think? It is a open set, close, sorry, it is a, what it is?
It is not domain.
It is not a domain, because this is not open.
Open.
Since it is not open, so therefore this is not a domain. You can say it well as a region, that's not a problem, but you cannot say it as a domain. Chalo, last question, try to do this. What do you think about this S5? given by all those Z belongs to C, and a few things today I'm also going to write, so that from tomorrow we can start with some sequence in series term, and then we'll see what to do. Real part of Z modulus. What do you think?
नहीं
हाँ जी.
नहीं समझ आ रहा है ये सेट तो
अच्छा, imaginary modulus of Z and real modulus of Z. Think about इसको सोचो and think about this. दोनों set I'll give you.
पॉजिटिव वैल्यू
Only one thing you have to do, you have to make it on, take your pen and paper and make the region first, and then and then you'll be able to understand that whether it is only a region or domain. Okay, and third, I'm giving you all these three. I'm giving you as a homework. Try to do them, and if you are not able to get, I'm going to do tomorrow. Don't worry. So that you also should do something. The modulus of Z less than Z minus of A. Okay, so these three I'm giving you as a homework. Try to do them. Nahi hota, then I'll do anyway, but just think about it, because I have certain more definitions to it. So एक बार के लिए for once you know what is open and connected. I hope it is clear. No, imaginary Z kuch nahi. Just take imaginary Z as Y. And what is it? Real Z? Real Z is X. So modulus of X less than modulus of Y you have to make. So what is modulus of X less than modulus Y? Just divide it into two parts. Take Y uh, greater than 0, then X greater than 0, and all those things you have to do. I'll help you anyway, but एक बार try to do on your own self.
Yes, sir.
Okay, these three things. Now there are few things. Boundedness. Now what is boundedness here? So set S, which is a subset of C, is said to be bounded. It is said to be bounded if there exists a R greater than 0 such that S is contained in a closed disk R. So basically, what does it mean? It means that if you're saying that your region S, or simply region S, or subset S is a closed set, then it must be contained in some closed disk, or otherwise you can write that all the elements belongs to set S. You can write in this fashion, less than some M. So for all Z belongs to S, if modulus of Z is less than M and M is greater than 0, we say that the set S is bounded. Or otherwise, we can say that if set S is contained inside some closed disk of radius R, so obviously all the elements would be less than the radius of this particular disk. All the elements contained in S would be having having the magnitude less than R. So clearly this is also a way of defining boundedness. This is also a sense of defining boundedness.
Yes,
is that clear? So if we are saying geometrically that S is contained inside a closed disk, this you know, this I think you know now what is del R. It is equals to what? It is equals to Z minus mod less than R. So if your S set is contained inside this, so obviously all the elements of set S will have the magnitude less than R. है ना? All the elements will have a magnitude. All the elements in S will have a magnitude less than R because it is contained inside that closed disk. So clearly S is bounded.
Yes, sir.
Okay, and a set S. And otherwise, this is also how you define in real also. This is the same here, that if S is a bounded set, then all the elements contained in that set, the modulus I can write less than M, where M is a positive number. A set S is said to be unbounded if I cannot find any such disk. So if is unbounded, if it cannot be enclosed, within a what you can say closed disk. So I'll not write closed disk. I'll simply use the notation closed disk of radius R, with R is greater than 0. So then it is said to be unbounded. Is that fine?
Yes, sir.
For example, if you want to see, this is an unbounded set. So if real part of Z modulus is less than B and greater than A, what does it mean? It means that X can lie between what? X can lie between A and B, including B. But what about imaginary part? It can take any value from, y can take
Infinity.
any value from minus infinity to plus infinity.
Yes.
So this will form a vertical strip. So therefore, this is unbounded. Is that clear?
Yes, sir. Yes, sir.
मैंने example इधर से दे दिया, otherwise I can take many example, but this is the last thing that we've done. So real part of z less than equal to b and greater than a, what it would be? It would be a vertical strip, and this vertical strip, and this is included, no? So this is, I'm writing, this is included. So b is included, but a is not included. But anyway, your y would lie from where to where? So y can lie from minus infinity to plus infinity. So clearly, this is an unbounded. This is an unbounded set. Is that fine?
Yes, sir.
Now, another definition: the sets which are closed as well as bounded in C are called as compact sets. या फिर are called as compact in C. Okay. So I'm just giving definitions. Okay. So the sets which are closed and bounded in C are called as compact sets in C.
सर जैसा इसका रियल में प्रूफ तो वैसा कॉम्प्लेक्स में भी प्रूफ होता है कि
बिल्कुल बिल्कुल वैसा ही होता है. But that goes in topology. So अभी हम लोग उतना डिटेल नहीं जा रहे. Otherwise, that I teach in metric spaces and topology. That is a different thing. But right now, you should be acquainted with all these terminologies. Okay. So वहां पे तुम उसको हेने-बोरल नाम से पढ़ते हो. Here I'm writing the sets which are closed and bounded in C are called as compact set in C. Right?
Yes, sir.
Is that fine till now?
Yes, sir.
Okay. So for example, if you really want to see, a closed disk is a compact set. Is that fine? Because it is bounded also. Sorry, a closed set. Sorry, it is a closed plus bounded set. So therefore, it is a compact set in C. Is that clear? A closed disk. See, a closed disk is closed. Closed not in the sense of closed because it contains all its limit point. Okay. So closed disk that is mod z less than equal to R is a closed set in the sense that it contains all its limit point and it is bounded also. So therefore, this set is a compact set in C.
तो एक्चुअली कॉम्पैक्ट होता क्या है कॉम्पैक्ट मतलब
बस कॉम्पैक्ट का यहाँ पे जो मतलब है इट इज दिस वन यू हैव टू रिमेंबर दिस एक बार को कॉम्पैक्ट का मतलब a set which is closed and bounded I'll say compact here. Okay, otherwise again वही मैं तुमसे कह रहा हूँ compactness समझना है then it is a different concept and we have to see it in the more generalized sense in metric spaces, so it will become a big topic. So right now don't go there, अभी के लिए सिर्फ इतना समझो. Okay, we'll do all those things na, we'll do all those things in general topology, but right now just don't go into that side. Just understand, if I'm saying a set which is closed and bounded in C, then it is compact in C. Okay, is that fine? See, right now what is the point? अभी हम आगे पढ़ेंगे ना. So the point is that in complex analysis we are going to use these terminologies time and let's say a continuous image of a compact set is compact, so here also it remains the same. So continuous image of compact set is compact in C also. So we have to use certain statements, so we'll use it. अब तुम बोल रहे हो what is compactness? So compactness is a big topic. It is a topic that we are going to cover in general topology or metric spaces. So wait for that time. अभी के लिए we'll keep it only restricted to C. Okay, we'll do it. Don't worry. In metric spaces, we'll do. But right now, and similarly, connectedness also. Okay, connectedness also. This is not how we will do. We'll do it in a greater detail. But right now, just understand by whatever I have put in. Okay,
Yes,
so that things will not get complicated. Otherwise, it will become very complicated, and we'll forget what are we doing right now. So we are doing right now complex analysis. We have to stick to that particular scenario. Okay. Now see, complex plane is not compact. Why it is not compact? Because entire complex plane. So what is complex plane? Complex plane
not
is
bounded.
not bounded. Very good. So it is not bounded. So therefore it is not compact. So it is not compact. So in general, we can say that this complex plane or with the usual metric, that is with usual Euclidean metric, I would say, is not a compact metric space also in general. So we'll do all these things. Don't worry. I'll teach you metric spaces, but right now my target is to finish things in this sense. That we'll do separately. Is not a compact metric space. Okay, so I hope it is clear. Now a little bit about countable and uncountable, because those are two things that we are going to use again and again. So countable simply means a very simple terminology I'm giving. If there is a one-to-one correspondence, if there is a one-to-one correspondence with this with natural number or a segment of natural number. So segment of natural number would give finite sets. And if the set has a one-to-one correspondence with n, we'll get countable sets, and this will be infinite countable. But even if the sets are infinite, we'll say that sets are countable if there is a one-to-one correspondence with n. A finite set is fine. Let's say if there are some numbers here, I can always associate it with some segment of natural number. But if I can associate, see, the point is this, that infinite sets, whether they are countable or uncountable, how do we define them? If we are making a correspondence with n, then we say that sets are countable. Otherwise, sets are uncountable. Okay.
Yes, sir.
Okay. A little bit already you might have known sets of what is rational number, countable, uncountable? Countable. Okay. How are irrational number? They are uncountable.
No.
Okay. What are real numbers? They are uncountable. You know all these things or you do not know all these things?
No, sir.
Okay. So set of rationals are countable. This will prove. We are not going to prove right now. We just remember this. Set of irrationals are uncountable. Set of all reals are uncountable. How they are done, that's a separate topic of countability. But remember, any set which is countable. So if somebody says set of even integers, is that countable or uncountable? These are countable because you can always write fn is equal to 2n and you can verify that this is 1, 1 and on 2 set. So that's not a problem.
Yes.
Okay. This requires something called as Cantor's diagonalized argument to prove that whether set of rationals form a countable set or not. So that we can do by Cantor's diagonalization argument. By Cantor's diagonalization argument. That we'll see some other day. But right now, just remember that the set of rationals form a countable set of irrational form an uncountable set, R is an uncountable set, the set of even integers form a countable set of odd integers also form a countable set. Set of integers itself is a countable set. I hope it is clear. So all these things are basics. So basically, right now I'm rushing because you don't have to. We are not here to study topology. We are here to study complex analysis. So right now we have entered, I think, 6th lecture or 5th lecture, and we are right now only doing basics. So when are we going to start with analytic functions and Cauchy-Riemann conditions and all those things? So therefore, the task is that if you want to read a book by your own self, at least you should know all these things. Otherwise, you start a book, you start doing some self-study on your own, then all these things will create a difficulty. So I hope it is clear till now. Tomorrow we are going to do a few questions on connected sets and disconnected sets and whether a particular region is a domain or not. A few questions I have already given you. 3 of them I've already given you. Do all these 3 questions, and then we'll try to start analytic function in 3 to 4 days. And once we start analytic function, there lies the heart of the complex. So most of the times, even in exams, also most of the questions start coming from analysis part, not from the this topology and what you can say numbers. So you will not find many questions from here. But overall, it is very important. So you should not forget it, and you should not skip the things like these. Okay.
Yes, sir.
Chalo, take care. We'll take.